Welcome to Science Simplify, where complex science becomes clear and easy to understand. We are glad to have you with us today. In this video, we are going to explore one of the foundational principles in physical chemistry and gas behavior, Graham's law of effusion and diffusion. This law was formulated by the renowned Scottish chemist Thomas Graham in 1848, and it remains essential to our understanding of how gases move and interact. Whether you are a student, an educator, or simply someone curious about the science behind everyday phenomena, this video will guide you step by step through everything you need to know about Graham's law. We will break it down into clear sections: the definition, the distinction between diffusion and effusion, the mathematical formulas, the molecular basis behind it, and real-world applications. Let us begin. Section 1. Definition and key principle. Let us start with the core definition and key principle. At its core, Graham's law states a simple but powerful relationship. At a constant temperature and pressure, the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass or density. What does this mean in plain terms? It means that lighter gases travel faster and heavier gases travel slower. This fundamental principle applies universally to all gases and forms the basis for understanding gas behavior in both chemistry and physics. Section 2. Diffusion versus effusion, key distinctions. Next, let us clearly distinguish between two closely related but different processes: diffusion and effusion. First, let us look at diffusion. Diffusion is the gradual mixing of molecules due to random thermal motion. Imagine two containers connected by a valve. The left container contains red-colored gas particles, and the right container contains blue-colored gas particles. When the valve opens, the particles gradually mix together over time. A great real-life example of this: smelling perfume. When you spray perfume, the scent molecules spontaneously spread through the surrounding air and reach your nose. That is diffusion in action. Now, let us look at effusion. Effusion is the escape of gas particles through a tiny pinhole into a vacuum or an area of lower pressure. Imagine a container filled with mixed gas particles, where some particles escape through a single small opening on the right side. A perfect real-life example of this is air escaping from a flat tire. The pressurized air molecules inside move through a small puncture hole to the outside. The key difference to remember is that diffusion is all about gases mixing together, while effusion is about gas escaping through a small opening. Section 3. Mathematical representation and formulas. Now, let us look at the mathematical side of Graham's law. To make this perfectly clear for voiceover readout, we will express the equations exactly as they are spoken. The core formula is written as rate 1 divided by rate 2 equals the square root of molar mass 2 divided by molar mass 1. This mathematically shows that the rate is inversely proportional to the square root of the molar mass. We can also express this relationship using densities or time. When comparing gas densities, the formula is written as rate 1 divided by rate 2 equals the square root of density 2 divided by density 1. When measuring the time required for a gas to move, the relationship is inverted because a faster rate means less time is taken. Therefore, the formula becomes rate 1 divided by rate 2 equals time 2 divided by time 1, which equals the square root of molar mass 2 divided by molar mass 1. These formulas allow you to compare the rates of two different gases or calculate unknown molar masses, making this law highly practical in laboratory and industrial settings. Section 4. Molecular basis and kinetic molecular theory. To truly understand why this happens, we can connect Graham's law to the kinetic molecular theory. The key underlying principle is that at the exact same temperature, different gases possess the same average kinetic energy. The fundamental formula for kinetic energy is kinetic energy equals 1/2 mv squared, where m represents mass and v represents velocity. For two different gases at the same temperature, their kinetic energies are equal, which allows us to write the equation as 1/2 m1v1 squared equals 1/2 m to v2 squared. When we simplify this equation by removing the 1/2 from both sides, it becomes v1 squared divided by v2 squared equals m2 divided by m1. Taking the square root of both sides gives us the final velocity relationship. v1 divided by v2 equals a square root of m2 divided by m1. This clearly demonstrates that the ratio of molecular velocities is directly connected to the inverse ratio of their molar masses. This mathematical proof explains exactly why lighter gases move faster. It is rooted in the fundamental physics of kinetic energy and molecular motion. Section 5. Real-world applications. Graham's law is not just theoretical. It has crucial practical applications in science and industry. The first application is comparing helium versus air balloons. A helium balloon has a light molar mass of 4, while an air-filled balloon has an average molar mass of 29. Because helium is much lighter than air, it effuses and diffuses much faster through the pores of the balloon material. As a result, a helium balloon deflates much faster than a standard air-filled balloon. The second application is uranium enrichment and isotope separation. This industrial process involves separating uranium to 35 hexafluoride from the heavier uranium to 38 hexafluoride using a centrifuge machine. Due to the very slight difference in their molar masses, the lighter isotope travels slightly faster through physical barriers. This exact principle is critical globally for nuclear fuel processing. The third application is determining an unknown molar mass in a laboratory. By using a specialized U-tube apparatus, an unknown gas can be directly compared against a known standard gas. By accurately measuring their relative effusion rates, scientists can easily calculate the precise molar mass of the unknown gas. This remains a common and highly reliable technique in analytical chemistry. Conclusion. Let us recap the main points we have covered today. First, Graham's law states that the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass. Second, diffusion is the mixing of gases, while effusion is the escape of gas through a small opening. Third, the mathematical formulas allow us to accurately compare gas rates, densities, times, and calculate unknown molar masses. Fourth, the kinetic molecular theory explains the underlying physics, showing that lighter molecules must move faster to maintain the same average kinetic energy at a given temperature. Fifth, real-world applications range from everyday observations like deflating balloons to critical industrial processes like uranium enrichment and laboratory chemical analysis. This law, formulated by Thomas Graham in 1848, continues to be a cornerstone in chemistry and physics education. Understanding it helps us grasp how gases behave in nature, in laboratories, and across major industries. Thank you for watching Science Simplified. If you found this video helpful, please like, share, and subscribe for more clear and concise science explanations. See you in the next video.